Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss interference in wedge shaped film and plane parallel film. Let's begin. Interference in wedge shaped film. What is a wedge shaped film? A film whose thickness is not constant is a wedge shaped film. How the thickness varies? The thickness of the film is 0 at one end and goes on increasing towards the other end. How we form a wedge shaped film? Let two glass plates touching at one end and separated by a thin sheet of paper at the other end that form a wedge shaped film. Here is a glass plate. Let that glass plate be OA, and another glass plate let OB. These two glass plates inclined at an angle theta, and these two are separated by a thin sheet of paper. Thin sheet of paper having the thickness T. That is a glass plate. Here is the glass plate. Let that portion, just like a thin film of air enclosed between the plate. This one is a paper sheet having the thickness T. Let we go forward to the analytical treatment, means how the interference pattern is observed when a light is incident on that of wedge shaped film. Let us we suppose that the refractive index of the film that we consider, let mu. Analytically, let we derive. Here we take OA glass plate, another one let OB, and it has the thickness T and refractive index let mu. Thickness here is small t. That thin film is illuminated by a light from the sodium lamp. From the sodium light is illuminated to that of wedge shaped film, and that light is act as the source of monochromatic light having, let the wavelength of that light be lambda, and that light is coherented by taking a slit placed in front of that of light. Let you take that light is incident on that of wedge shaped film. Here it makes the angle of incident I. When the light ray at CD incident on a thin film, it will suffer the division of amplitude at that of upper surface of that of thin film, and the interference will occur between the rays of light reflected from the top and bottom of that of film. Here the separation is let theta, that light is incident here, so some of the amplitude gets reflected some get transmitted or refracted. Angle of refraction let R at that of surface, that surface incident at E. Then again at that of surface, again division of amplitude, that light get reflected and again transmitted. At that of surface, light again refracted or transmitted. It is due to DG and FS, we have an interference pattern on that of screen. So let we calculate what be the path difference in between these two. Draw a perpendicular at I. So the path difference, the path travelled by that of Fs DE EF, that is multiplied with that of refractive index, and subtract the part Di with the path difference between these rays DG and Fs. The path difference is same as you derived in case of interference in thin films, but again as the figure changed, let we show that derivation is same as this derivation. Now we write it, path difference delta is equal to refractive index DE plus EF dE plus EF minus that portion dI. Let I draw a perpendicular from the point F to DE. That intersect at the point J. So DE can be written as DJ plus JE. So mu is equal to DJ plus JE plus EF minus DI. As we write it, DE is equal to DJ plus JE. Here, look at that figure. This is the angle of incident, that is the angle of refraction. So the sum of the entire angle will be 90 minus I, as angle of incident is equal to angle of reflection. So that is I, that portion will be I. So the entire portion will be 90 minus I. That angle is 90, that angle is 90 minus I. So this angle is same as I. Okay. Here I use the Snell's law concept. That is for path difference. Let equation number 1. From Snell's law, mu is equal to sin I divided by sin R. So in that of triangle, as we consider IFD, sin of this angle is equal to DI divided by DF, DI divided by DF. Again sin of R, sin of R is equal to that portion of angle is equal to R. How? Look at that particular figure. Here this is the angle of refraction, small r. So that entire angle is equal to 90 minus R. 90 minus R, 90 minus R plus 90. So that angle will be smaller. So sin R in that of triangle DFJ, sin of R is equal to DJ divided by DF, DJ divided by DF. Here DF cancel out. We have DI divided by DJ, or DJ into mu is equal to DI. So DI is equal to mu times of DJ. Now the equation can be written as, in place of DI I substitute mu DJ. For equation 1 becomes delta path difference is equal to mu DJ plus JE plus EF minus, that is mu DJ, or delta is equal to mu DJ plus mu JE plus EF minus mu DJ plus mu DJ minus mu dj cancel out. We have delta is equal to mu je plus ef, je plus ef je plus ef. Now from that of figure, that portion will be T, that will be the thickness. Now EF we draw that side is equal to EK. So EF is equal to EK. I elongate that line here. EF is equal to EK. EF is nearly equal to EK. I draw it. So delta is equal to mu EF plus EK. EF je EF, in place of EF I substitute EK, je plus EK, or delta is equal to je plus EK, that is jk. Look here how I draw that one. For what region? What be the region? Let I have to congruent that angle EF this to that portion angle. So that side must be equal to this side. That will be the thickness here. I elongate that side. That angle is theta. This angle will be theta. That angle is the outside angle of the triangle D. Let L E. So that angle will be R plus theta. That angle will be R plus theta. Look here, that side, that normal, both are parallel. So that angle is equal to this angle. That angle will be R plus theta. That angle is equal to this angle. That is the line. That is that line. First, that angle will be theta. This is the outside of that triangle, so that angle will be R plus theta. That angle is equal to this angle, that is R plus theta. Now our task is to get jk. Look the side JFK. That angle is R plus theta. This is 90 degree. So cos of R plus theta in the angle JKF, cos of R plus theta is equal to that side divided by this side. Right here, in triangle JFK, cos of r plus theta is equal to fk divided by jk. Fk, that side t, again this also t, 2 times of t, 2t divided by jk. Our aim is to calculate jk, or jk is equal to 2t cos of r plus theta. Now in place of jk we substitute the path difference delta is equal to, here is the mu times of jk, mu 2t cos r plus theta. Since the reflection from denser medium, then there will be additional path difference, and that path difference is plus lambda by 2. An additional path difference of lambda by 2 is introduced due to reflection from denser medium. Thus, path difference delta is equal to 2 mu t cos r plus theta plus lambda by 2. That will be the path difference. Using that path difference, we can easily get the condition for maxima and the condition for minima. For maxima, we know the path difference is integral multiple of lambda. Delta is equal to n lambda, where n starting from 0, 1, 2, 3 like this. Delta, that is 2 mu t cos r plus theta is equal to 2n minus 1 lambda by 2. Look that up term. Here the angle r, angle of refraction, is very small, that is nearly equal to 0, and the inclination angle also very small. So r plus theta is nearly equal to 0. Cos 0 is equal to 1, that will be the maximum value of cos. When r is negligibly small, r nearly equal to 0, then the angle theta is very small. Therefore, cos of r plus theta means cos 0 is equal to 1. Now for air film, that portion let be air, so the refractive index is equal to 1 for air film. Mu is equal to 1. Then the condition for brightness, condition for maxima or brightness, that is 2 mu t cos r plus theta is equal to 1 is equal to 2n minus 1 lambda by 2. Again mu is equal to 1, or 2t is equal to 2n minus 1 lambda by 2. That be the condition for brightness or maxima. For that reason, I say the expression for path difference is same as we derived in case of thin films. Here r plus theta is very small, that is why the condition will be same, as the path difference is equal to 2 mu t cos of that angle, as we derive in that particular case. Now for minima, the path difference is the odd multiple of lambda by 2, where n from 0, 1, 2, 3 like this. The value of delta 2 mu t cos r plus theta is equal to same thing 2n plus 1, since n is the integer, look here, lambda is equal to delta is equal to 2 mu t cos r plus theta plus lambda by 2 is equal to n lambda. So in that of side n lambda minus lambda by 2, so 2n minus 1 lambda by 2, as delta is equal to additional path difference lambda by 2. Same thing here, plus lambda by 2 is equal to 2n plus 1 lambda by 2, or 2 mu t cos r plus theta is equal to 2n plus 1 lambda by 2 minus lambda by 2, or 2 mu t cos r plus theta is equal to n lambda. Again for air film, mu is equal to 1 and cos of r plus theta is nearly equal to 1. We have that expression for path difference change to 2t is equal to n lambda. That will be the condition for minima or for dark fringe. we obtained. Now let that sheet of paper having the thickness T is at a distance of x from the origin, from the starting point of that of wedge shaped film. Gradually the thickness increases. So T is varies with respect to x. So tan of this angle, tan of theta is equal to T by x. Or theta is equal to T by x, as tan theta is nearly equal to theta for small angle. Therefore, the thickness T is equal to x into theta. Now, the condition for maxima and minima, means for darkness and brightness, hence for brightness two mu x theta, here is a term mu will be there, is equal to 2n minus 1 lambda by 2, and for darkness again 2, here also okay, that when there will be no such air medium, that expression will be no mu. For darkness, here mu is introduced, so 2 mu x theta is equal to n lambda, that for brightness and that for darkness. It has the refractive index mu. In these two expressions, we take air film as mu is equal to 1. Now, we have to calculate the fringe width. Fringe width if the distance between two consecutive dark or bright fringe, let you take nth dark fringe, nth dark fringe, the distance can be taken as xn from the edge for nth dark fringe, xn be the distance. Similarly, n minus 1th or n plus 1th dark fringe, the distance can be taken as x n minus 1 from the edge. Therefore, xn is equal to n lambda divided by, as you take for dark fringe, 2 mu theta, and for n plus 1th, x n plus 1 is equal to n plus 1 lambda divided by 2 mu theta. Therefore, fringe width beta is the distance between two consecutive dark fringe or bright fringe. We consider here the dark one, n plus 1 minus xn is equal to n plus 1 lambda by 2 mu theta minus n lambda by 2 mu theta, or beta is equal to lambda divided by 2 mu theta at the fringe width in case of wedge shaped film having the refractive index mu. So, here we discuss about how interference pattern is observed in case of wedge shaped film. This is a wedge shaped film, and analytically we show how the path difference and condition for maxima and condition for minima, condition for maxima and condition for minima when the angles are very small and the refractive index is 1, which is for air film. The distance at which the dark or bright fringe is obtained, that be the expression. Next, fringe width in case of wedge shaped film. Now, we discuss about the interference in plane parallel film. As we derived the interference in thin films for refracted light and transmitted light, that also an example of plane parallel film. So, what is plane parallel film? Plane parallel thin film is a transparent thin film of uniform thickness that bounded by two plane parallel surfaces. How the interference pattern we observe here? When a light is incident on a parallel thin film, light gets partly reflected from the top surface and gets partly transmitted into that film. If we take the plane parallel thin film, it is a thin film. All over that surface the thickness is same, and that thickness be T. It has let the refractive index be mu. When light ray is incident here, so the division of amplitude concept is used here. Some of the amplitude gets reflected and some are transmitted or refracted. Again at that of surface, reflection and transmission occurred. Finally, at that of surface the light gets transmitted, that is the reflected waves, and we observe the interference pattern. Also, a small portion of the transmitted ray is reflected back into that of film by the bottom surface, that figure of that of thin film, and the remaining portion of the light is transmitted from the lower portion. The thin films have a tendency to transmit the incident light strongly and reflect only weakly, and the intensities of the reflected rays reduces as the negligible strength after suffering two reflections. Here the amplitude here the amplitude, and gradually the amplitudes decreases. So, we consider only the first two reflections, and these two reflections are derived from the same incident ray, but appear to come from the two sources. These are appear to come from the two sources that be the S, that be the STS, and these two sources are the virtual sources and which are supposed to be coherent, and the reflected waves travel parallel path and they interfere at infinity, and this is called the two beam interference, and we have the interference pattern that is same as we discussed in case of thin films. So, with the help of this visual exercise we understand how interference pattern we observe in case of wedge shaped film. And interference pattern in plane parallel film. The expressions are similar to that of interference in thin films for reflected and refracted light. So, with this useful and informative notes, let me wind up this session. Thank you.